Hi everybody, Mr. Bennett here. We're just going to go through a question about the surge function. I'm going to do the one from review set 5B from page 199. So question 8, you've got this information which is given to you in the table, which is looking at the effectiveness of a arthritic pain drug. And so what we need to do first of all is put this information into a table. So I've already done that, and you can see the process of doing that is to go into stat, into edit. I'll put those values in there. And so therefore the next stage would be from that, once you've got that, is to turn your stat plot on and graph this information. So come down to making sure that's a scatter graph, going down to the next bit, making sure we've selected our two lists, and I've already done that. Next part is to go to zoom. We'll get out of there, sorry, go to zoom and go zoom 9, which is stat fit, and you can see that does model the surge type function which we were expecting to see. Now the next bit is to try and actually model that, so we're going to go through a couple of processes to do this. The first step is to go back to your stat button and go to edit. And remembering what we need to do is find the ln of list 2 over list 1. So if I put that value in there into ln, we use our list 2 divided by list number 1 and enter. That should fill that down. Oh, we've got a 0, can't divide by 0, so let's just go to what we need to do. If we quit out of there, sorry, going to our stat button, edit, what we need to do is go to both of our columns here and delete our 0 term. So if we delete both of them, it should now work. So going up to there, ln of simply list number 2 divided by list number 1 and enter. We've got our values there. So what we need to now do is need to go and simply graph that data, try and find a linear representation of that. So we're going to change our graph to be list number 3. I'm going to do the same process again. Go to our zoom button, zoom 9, and you can see it's a nice straight line. So if we go to our stat button, we can actually work out what the equation of that line is by going down to number 4. We're using our list number 1 and using list number 3, and I'm going to store that. Actually, I don't need to store that. Let me go calculate. Alright, so it tells us that we've got a very good correlation coefficient there. Our A value is in fact going to be equal to negative 0.3628. That will be enough details, and our B value is 3.2775. So if I go back to my Word document, so what we've got here is we've got a graph, and I'll just show you what we've really done. We've done a graph of, it's a bit ugly, we've got a graph of ln of E on T versus T. Alright, so we've got a straight line graph. It goes something like this, going down like that, and the equation of that graph is in fact given by the equation y is equal to negative 0.3628 T plus 3.2775. So that is the equation which sort of gives us a very linear equation there. What we need to do is we need to use that relationship to find the equation of E versus T. So I'm going to substitute those values in on my graph, and they are going to be ln of E on T is equal to, that's my y value, is equal to simply minus 0.3628 3628T plus 3.2775. Now the rearrangement of this equation is in fact putting these both all to the power of e. So when we do that, that becomes ET over there, and this side becomes e to the negative 0.3628T plus 3.2775. We can now use our indices laws and we can rearrange that, and we can say that's equal to e to the 3.2775 times by e to the negative 0.3628T. Now if I go to my calculator and work out this first part over here, then what we will see is that will give us a value that we can write in front. So e, I'll just quit out of there. So e to the power of 3.2775 is actually equal to 26.51. Right, 26.5. So for our model, that's what we're going to use. So that's now equal to our function e to the t is equal to 26.51 t. We bring our t up from the side over here, and then that's e to the minus 0.3628T. So that's our model that should hopefully fit this particular thing over here. So the next step, what we've got to do is in fact go to our calculator and put that back into the calculator and graph it and see how good a model it actually is. So if we go to our calculator, so go to our y equals, we're going to put that model into the calculator, which is 26.51x times by e to the negative 0.32, sorry, negative 3.628x, and just enter that. I don't know if that worked. I'll need to actually do that again. Sorry. 26.51x times by e to the negative 0.32 negative 628x. Enter. Alright, so that's our function. Go back to our y equals. I'm going to go to our stat plot. We need to now change that back to list number 2. Alright, I'm going to go zoom. Go zoom number 9, which will allow us to do the graph, and you can see that's almost a perfect correlation model there for our graph, so that's great. Alright, so let's go back to our textbook question. Alright, so we've done our graph of that, we've found our model. Part C is what time is the drug most effective? Well, that equates to the maximum drug in your system. So if we go back to our calculator, we can calculate our maximum by doing our G-calc, going to number 4, scrolling across to the side over here of the maximum. Right, and go enter, go to the right hand side of that. You can either scroll across or just use a value, type in a value, that will do. Enter, so we know it's going to be most effective. We get a level of 26.88 when it's 2.76. Alright, so going back to there, so part C for that, so maximum level of 26.88 units when X or T, should use T, shouldn't I? Because it is time. So time is equal to 2.76 hours. Now you can also work that out to the nearest minute by simply going to your calculator and going 0.76 divided by 60, actually times by 60, times by 60, so it's going to be 45 minutes and 0.6 of a second. Alright, so gives you a bit of an idea about how you're working that. So that's 2 hours 45.6 minutes. Alright, so the last part of this question asks us to work out when the drug is most effective, when the units are in fact over 12. So at what time after taking the first capsule should the next capsule be taken? Alright, so what we need to do here is we need to actually find those times on our graph where our drug is in fact over 12. So if we had a line over here as 12, alright, so then what we're expecting to do is we need to take our next drug prior to that wearing out. So we'll do something like that. Alright, so we need to find this time here, and we also need to find that time there, so we can actually work out. So if we go back to our calculator and go to our graph, we can put in another graph line over here which is 12 and graph that. We can find the intersect points of those two things by going to graph, going down to number 5, enter, and we'll find that time there to be equal to 7.875. The next one we can also find, and if we go to calc, we go to our intersect point, number 5 again, and we can scroll back over here. We have to go on the other side of that maximum if we want to find the other point of intersection. Right. So enter, and we'll find the other point there. It appears to be 0.553. Alright, so that's our time that we've got. If I go back to our curve over here, so our first value over here, that is actually 0.553. This occurs here at a time of 7.875. So if I take the difference between those two, that will tell me when I need to, how long after I've started taking my medicine I need to take that. So if I do 7.875, take 0.553, that will give me an answer which is approximately equal to 7.322 hours. Now if you also go and convert that to minutes, that works out to be 7 hours and 19 minutes. So that's the time that I'd actually need to take that after my beginning time. I hope this helps you in terms of looking at those questions. Obviously if you need some more help, you need to catch me in class and I will go through that in a bit more detail. It is quite a long question, but it's got some steps. Once you get the idea of what you've got to do, you can get through that quite quickly. Anyway, good luck with those, and I'll catch you next time.